Good morning, everyone. I'm going to defend my thesis, cache-aware real-time virtualization. Recently, virtualization has gained a lot of traction in real-time systems. This trend is driven by two facts. First, real-time systems are becoming increasingly complex. Take our car, for example. We are having more and more features integrated into our car. This requires higher performance and also increase the size, weight, and power consumption of the entire system. Meanwhile, the hardware is becoming more and more powerful. For example, we are having more and more cores integrated into the single chip. With virtualization technology, we can integrate the legacy systems into virtual machines on more powerful hardware platform. This helps us get better performance because we have a more powerful hardware and also help us to reduce the cost of the entire system. However, this also raises new challenges in achieving the timing guarantees required by real-time systems. One of the challenges is introduced by the shared hardware components in a multi-core platform. As we know that in a multi-core processor, the many hardware components are shared. Take cache, for example. Each core can have a private cache. All tasks on the same core share the private cache, and different cores share a last level shared cache. The tasks running on different cores can access the shared cache. When these tasks access the same cache area, they may evict out each other's cache content, causing extra delay for them to access the results. This extra delay can increase task's execution time, which may eventually make the task miss deadline. In addition, in order to analyze if the tasks can meet their deadline under the presence of this shared resource interference, we need to know tasks information. However, due to VM abstraction, task information in VMs is not available to system designers, which make it harder to analyze the timing behavior of the entire system. In order to bring virtualization technology into real-time systems, we have to provide the timing guarantees for virtualization systems. We call this as real-time virtualization. It requires two key techniques. One is the analysis. We need to analyze the system's timing property. For example, given a system, we need to determine how many cores we need to make sure all tasks in the system will not miss their deadline. We also need the resource management technique to regulate hardware resources for VMs and tasks to improve the system's timing property. For example, given a system, we need to say if we can manage the resource in a better way such that we can meet the system's timing requirement with less number of cores. There exists some work in real-time virtualization. For example, we have the compositional analysis to analyze the system's timing properties. We also have the real-time schedulers in hypervisor and operating systems to regulate the CPU resource for VMs and tasks. However, existing approach primarily focus on the CPU resource and ignore other type of resource. CPU cache is another important resource that can affect the system's real-time performance, and its behavior is harder to analyze or manage. The current work in real-time systems primarily focuses on managing or analyzing the cache resource for non-virtualized environment. Due to the virtualization abstraction, the work can now be directly applied to real-time virtualization. For more general virtualization systems, researchers primarily focused on improving the system's average performance instead of the worst-case performance. So the work in virtualization systems can now be applied to real-time systems. In this work, we propose cache-aware real-time virtualization, which provides the timing guarantees for multi-core virtualization systems under the presence of cache interference. It has four building blocks. First, to analyze the impact of private cache overhead, we propose a private cache-aware composition analysis. To mitigate the interference incurred in the shared cache, we propose a dynamic shared cache management framework. To improve the overall system's performance, we propose a cache-aware scheduling analysis that co-schedules the cache and CPU results to improve the system performance. In addition, to further improve the system's performance, we propose a holistic resource allocation and analysis technique to allocate not only cache and CPU resource but also memory bandwidth resource in a holistic manner. In my thesis proposal defense, I have talked in detail about the first two building blocks. And in this talk, I will briefly go through the first two building blocks and spend most of my time talking about the holistic resource allocation and analysis. Now, let's have a look at the private cache overhead. Before we talk about our analysis, let's have a quick view of the background knowledge in real-time systems. In a real-time system, a process that performs some function is called a task. A task is activated once per period or when a new input arrives. At each activation, a task releases a job which must complete within a deadline. Each task has a parameter called worst-case execution time. It indicates the maximum amount of time the task may execute before it completes. We define task utilization as the ratio of the task worst-case execution time divided by its period. A task utilization indicates the amount of resource the task requires in order to meet its deadline. In a real-time system, we have a set of these tasks. We claim a system is schedulable if all tasks can meet their deadlines. In a real-time virtualization systems, we have a set of these tasks distributed into different VMs on a shared multi-core platform. In order to tell if all tasks can meet their deadline, we can use composition analysis. It has three steps. First, we can abstract the workload inside each VM into the VM's interface and transfer each interface into a set of vCPUs. A vCPU has a period and a budget, indicating the vCPU will serve budget time in each period. Later, after we get the vCPUs of all VMs, we can abstract this VM's workload into the system's interface. The system's interface indicates the minimum amount of resource to make sure all tasks can meet their deadline. If the hardware platform can provide the resource required by the system's interface, we claim the system is schedulable. There exists some work in composition analysis, but most of these works do not consider platform overhead. We call this kind of analysis as overhead-free analysis. As we know, tasks may interfere with each other through the shared resources, such as the cache resource. This kind of platform overhead is not negligible in practice. So without considering such platform overhead, the overhead-free analysis may underestimate the results required by the system and lead to unsafe analysis. For example, a system that's claimed schedulable by the overhead-free analysis may not be schedulable when we render. We may say some task miss deadline. So in our first work, we consider the overhead caused by the private cache resource and propose a cache-aware composition analysis to account for the effect of the cache overhead on the real-time performance of the real-time virtualization systems. I have discussed the details in the proposal defense. After we understand the impact of the private cache overhead, we look at how to handle the shared cache interference. As we know that tasks running on different cores may access the same cache area in the shared cache. And when this happens, they may evict each other's cached content and causing extra cache misses to each other. This extra cache misses can increase the task's worst-case execution time and make the task miss deadline. Simply analyzing such overhead can be very pessimistic, because literally speaking, a task can access any cache area at any time. Without managing the cache, the analysis has to assume the worst-case behavior of the tasks, and this leads to a pessimistic analysis result. So this motivates us to manage the shared cache to reduce the interference. We propose to dynamically manage the cache for tasks in a real-time virtualization environment. We let the hypervisor dynamically allocate cache to VMs, and let the operating system inside VMs to allocate cache to its tasks based on tasks' resource demand. This allows us to reuse cache that's no longer used by tasks. This can give us better utilization of the cache resource. And the running tasks and VMs can also have larger cache areas when they are executing, and therefore they can have smaller execution time, and thus better performance. To achieve the dynamic cache management, we use a hardware-based approach. We observe that recently more and more hardware processors start to support the hardware-based cache partitioning. For example, hundreds of Intel processors support the Intel cache allocation technology. This hardware technology can divide the shared cache into equal-size partitions and allows the system software to efficiently reconfigure the cache for tasks or VMs for cores. So based on this hardware feature, we propose vCAD. The key idea is to virtualize the cache partitions and expose virtual cache to VMs. Each VM is assigned for a virtual cache by the hypervisor, and to allocate cache partitions for physical cache partitions to a VM, the hypervisor links the virtual cache to physical cache partitions. The OS inside the VM controls the allocation of the virtual cache partitions to its tasks based on the task's resource demand. The operating system inside the VM cannot see the physical cache and only operate on its virtual cache. The operation on the virtual cache is trapped into the hypervisor and translated into the operation on the VM's physical cache partitions. So the high-level idea of vCAD is similar to the idea of virtual memory. But because of the unique properties of the cache hardware, there are several unique challenges to solve in order to provide the dynamic cache management without breaking the isolation required by real-time systems. I have talked about the challenges and the details in the proposal, so I will not talk about this. I will not repeat it here. We implement this design in Zen hypervisor and Linux and evaluate it based on the prototype. Compared to the no cache management mechanism, the static cache management supported by our approach can improve the system utilization by up to 3.3x. Compared to the static cache management, the dynamic cache management proposed by us can further improve the system's utilization by 3x. Now we have understand the impact of private cache overhead and mitigate the shared cache interference. In order to further improve the system's overall performance, we propose a holistic resource allocation analysis technique in my proposal. So as we know that when a cache miss happens at the last level cache, it will eventually lead to a memory request. The memory request from different cores will be reordered by the memory controller in order to provide a better average performance. The memory controller can provide two types of bandwidth. The guaranteed bandwidth, which is the minimum bandwidth the controller can provide at any time. And the best effort bandwidth is the peak bandwidth the controller can provide. If the total memory bandwidth requested by all of the cores is no larger than the guaranteed bandwidth, each core can get its requested bandwidth. Otherwise, we can no longer guarantee the bandwidth each core gets. How much bandwidth a core gets will depend on the amount of memory requests sent by other cores and also the type of memory request by the system. So in order to provide a deterministic memory bandwidth, we can make sure that the total bandwidth request is always no larger than the guaranteed memory bandwidth. To achieve that, we can divide the memory bandwidth into memory bandwidth partitions as we did for the cache partitions, and reserve memory bandwidth partitions for cores and make sure each core does not exceed its reserved memory bandwidth. To achieve that, we can let the hypervisor to monitor the memory request from each core and throttle the core when a core tries to send more requests than it's allocated for. So this design has been proposed and implemented in Linux systems. Here in the proposal, we implement it in the Zen hypervisor. Now, to mitigate the interference in the memory controller, we have the memory bandwidth management mechanism. To mitigate the shared cache interference, we have a VCAT, a shared cache management framework. To mitigate the CPU resource interference, we have a set of CPU schedulers implemented in our previous work. Now, in order to get a better performance, we have to allocate this three types of resource in a holistic manner. This holistic resource allocation problems can be challenged because there exists cyclic dependency in the allocation. For example, the workload we allocated to a core will determine how much resource, cache, and memory bandwidth resource should be allocated to each core, which will in turn affect the amount of workload that can be allocated to the core. In addition, the allocation on one type of resource can affect the allocation on another type of resource. For example, here we measure the kernel benchmark's execution time when it's allocated for different amount of cache resources and memory bandwidth resources. Each line here indicates the benchmark's execution time across different cache partitions under different number of cache partitions when its allocated number of bandwidth partitions is fixed. So if we look at the red line here, when the task is allocated for a very small amount of memory bandwidth resource, the task is very sensitive to the cache resource. But if we look at the yellow line here, when the task allocated for more bandwidth resources, the task becomes less sensitive to the cache resource. So in order to solve these challenges, we look at a concrete setting of the system. Here, we consider a core-level cache and memory bandwidth allocation mechanism. The task and vCPUs allocated on each core will have the same amount of cache and memory bandwidth partitions. We consider the partitioned EDF scheduling for the operating system inside VM and the hypervisor. So the tasks assigned to a vCPU can only be scheduled on this vCPU by the EDF scheduling policy. The vCPUs assigned to a core can only be scheduled on this core. We consider harmonic tasks whose periods are harmonic. Each task has a vector of worst-case execution time. For example, this table is part of the kernel benchmark's worst-case execution time. Each element here indicates the task's worst-case execution time when it's allocated for a certain number of cache memory bandwidth partitions and a certain number of cache partitions. And the goal here is to compute the resource allocation policy such that the systems become schedulable. This resource allocation policy needs to make several decisions. At the VM level, you need to determine how to map tasks to vCPUs and how to compute vCPU's parameters. At the hypervisor level, it needs to determine how to map vCPUs to cores and how much cache and memory bandwidth should be allocated to each core. In my thesis proposal, we have some preliminary solution for this problem. It solves this problem at the VM level with VM level allocation and VMM level allocation. At the VM level, it maps each task to a vCPU and synchronizes the release time of the task and its vCPU. This allows us to assign a task parameter to its vCPU to get the vCPU's parameters. Now we have a set of vCPUs. At the VMM level, we allocate resources for this set of vCPUs. We first cluster vCPUs with similar resource sensitivity. This helps us to allocate resources to vCPU clusters to improve the resource utility. The idea is that if a vCPU cluster is very sensitive to the resource, which means that its utilization decreases a lot when we allocate for a small amount of resources, then we will allocate more resources to this vCPU cluster. Otherwise, we will allocate as few resources as possible. Because the vCPU clusters may not be balanced after we allocate the resource, some clusters may have very low utilization, some may have very high utilization, which are harder to be scheduled. So we balance the workload across vCPU clusters so that it's easier for us to schedule the entire system. We iterate at the VMM level allocation until the systems become schedulable, or we no longer have any benefit in improving the system's schedulability. So because the preliminary solution reduces the two-level, so the preliminary solution reduces the two-level resource allocation problem to one level, and we also call this solution as flattened algorithm. To evaluate the performance, we evaluate the performance of this solution by comparing it with the optimal solution, which formulates the resource allocation problem as a mixed integer programming problem. And the evaluation is based on a randomly generated task set. We show that the flattened algorithm has a similar performance as the optimal algorithm does. So because later when we have more tasks in a task set, the optimal algorithm cannot finish within a limited amount of time. So we will use the flattened algorithm as an indication as the upper bound of the performance we can achieve. So although the preliminary solution performs well, it has some limitations. First, it didn't consider the cache overhead into the analysis. As we know that tasks on the same core may interfere each other on their shared cache. We should consider this to get a safer analysis. In addition, it requires the one-to-one task-to-vCPU mapping. This may not always be satisfied, because subsystem vendors may not want to leak their software's timing properties due to intellectual property concerns. So in the proposal, I propose three work. First, we want to consider the cache overhead into the analysis. Then, second, we want to explore other resource allocation algorithms that do not rely on the one-to-one task-to-vCPU mapping. After we have a better solution, we want to evaluate the effectiveness and efficiency of the solution. Now let's have so in the dissertation, we have solved all three proposed work. Now let's have a look at the first proposed work, how to consider the cache overhead into the analysis. As we know that tasks on the same core share the same cache area allocated to the core, so they can evict out each other's cache content and causing cache overhead to each other. This kind of overhead can be caused by three types of events, which are similar to the events that cause private cache overhead. So fortunately, we can analyze the impact of the overhead with a similar technique we used in our first building block, in our first work, private cache-aware composition analysis. Now, let's have a look at how to account for the effect of the cache overhead. The cache overhead, first, the tasks there exists one type of task-related event that can cause this cache overhead. This task is called task preemption event. It happens when a task preempts another task within the same VM. In this example, the green task runs on the core 1 using the partition shared cache to reduce its execution time. When another task in the same VM, actually on the same vCPU, is released, it may preempt the green task and evict the green task's cache content. Later, when the green task resumes, it needs to spend extra time reloading the evicted cache blocks, and the amount of time spent on reloading these evicted cache blocks is called one cache overhead. This one cache overhead value caused by the high priority task can be upper bounded by a parameter delta using the existing approach. We also observe that each high priority task can cause at most one preemption event in each of its periods. So to account for the effect of the cache overhead, we can inflate each high priority task execution time with one cache overhead. And we can analyze the schedulability of tasks on vCPU in the presence of cache overhead by analyzing the inflated tasks in the absence of cache overhead. If the inflated tasks are schedulable, then we can claim the original tasks are schedulable under the impact of task preemption events. So these are the task-related events. VCPU-related events can also cause cache overhead. The first type of event is called vCPU preemption event. It occurs when vCPU is preempted by another vCPU. In this example, the first vCPU is preempted by the brown vCPU. When this happens, the running task on the preempted vCPU, which is the green task, will stop execution, and the green task cached content will be evicted. Later, when the green task resumes, it experiences one cache overhead. As usual, the cache overhead caused by the high priority task can be upper bounded by parameter delta by using the existing approach. We also observe that each high priority vCPU can cause at most one preemption event in each of its periods. So we can inflate each high priority vCPU's budget with the one cache overhead to account for the effect caused by the vCPU preemption event. There exists another vCPU event that can cause cache overhead. It's called vCPU completion event. It happens when the vCPU exhausts its budget in a period and stops execution. In this example, the first vCPU is a partial vCPU, and its budget may deplete to zero when it's executing. Later, when this happens, the hypervisor will schedule another vCPU onto this core, and the new vCPU may evict the old vCPU's cached content. Later, when the green task resumes, it incurs one cache overhead. This one cache overhead can cause to the low priority vCPU I can be upper bounded by parameter delta by using some program analysis approach or measurement-based approach. With the delta, we observe that each vCPU can only experience one vCPU completion event in each of its periods. And to account for its effect, we can inflate each low priority vCPU's budget with one cache overhead. Now we have seen the two types of vCPU-related events. To account for the cache overhead caused by these two types of vCPU-related events, we can inflate each vCPU's budget with the overhead caused by them. Now we get the inflated budget and inflated vCPUs. We can analyze the schedulability of these inflated vCPUs to get the schedulability of vCPUs on core in the presence of the cache overhead. Now we have considered the cache overhead's impact into the analysis. How can we allocate the results without relying on the one-to-one task to vCPU mapping? So let's have a look at an intuitive solution first. In the preliminary solution, the one-to-one task mapping is introduced as a VM level allocation. And so we should focus on changing the VM level allocation to drop this assumption or constraint. We don't have to change the VMM level allocation. So intuitively, we can, at the VM level, we can group the task with similar resource sensitivity as we did in the VMM level, and pin pack tasks to vCPUs and calculate each vCPU's parameter using the composition analysis. Now we get a set of vCPUs. Since we have a cache-aware analysis, so we can consider such overhead impact into the analysis by inflating the tasks and vCPU's workload. Now we get the strawman solution, which does not rely on the one-to-one task to vCPU mapping. How does it perform? To evaluate the performance of the algorithm, we randomly generate tasks. The task's WCT pattern is similar to the WCT pattern of parsec benchmarks. To get the WCT pattern of parsec benchmarks, we profile each parsec benchmark under different number of cache partitions and memory bandwidth partitions. The tasks use the harmonic periods, which are uniformly distributed in an interval. And we define task reference utilization as its utilization under the maximum amount of cache and memory bandwidth resources. We define a task normalized utilization as the task's reference utilization times the slowdown factor. The slowdown factor is how slower the task will be when the cache is disabled and the memory bandwidth the memory controller always uses the worst case bandwidth. The normalized utilization is uniformly distributed in 0.1 to 0.4. We distribute the generated task to 4 VMs and allocate resource for hardware that has 4 cores, 20 cache partitions, and 20 memory bandwidth partitions. We set the cache reload latency at 0.14 milliseconds for each cache partition, which is based on our measurement on a real platform. So we increase the task set utilization and measure the fraction of schedulable task set at each task set utilization. We consider the flatten algorithm as the upper bound of the best as an indication of the best performance we can get. And we also consider the strawman solution we proposed. Here you can see that there's a big gap between the strawman solution and the flatten algorithm. This indicates that the solution does not perform very well. So we want to further improve the performance of the solution. We investigate the reason why the strawman solution does not perform that well, and found that the main reason is because of the high abstraction overhead when we compute vCPU's parameters using the regional composition analysis. The abstraction overhead is the difference between a vCPU's utilization and its task's utilization. This abstraction overhead can be high in some cases. Here I will show a very pessimistic case for the composition analysis. Suppose we have a task whose period is 10 and execution time is 1. To make sure the task is schedulable on vCPU with period 10, we need to set the vCPU's budget to 5.5 based on the composition analysis. This will cause an abstraction overhead as large as 0.45, which is 4.5x of the task's utilization. So this means that although the task's utilization may be low, the vCPU's utilization can be very high, which makes it very hard to schedule vCPUs at the hypervisor level. Why is it the case? How the abstraction overhead is introduced? So if we look at this task, its execution time is 1 and period is 10. This means that the task can be delayed for at most 9 time unit. If we assign the task's parameter to the vCPU, and because we cannot control the vCPU's resource supply pattern, in the worst case scenario, the vCPU may serve its budget at the beginning of its first period and as late as possible in the rest of the period. This makes the vCPU has a starvation interval as large as 18 time unit. During this starvation interval, the task will not get any results and will miss deadline. So in order to make sure the task is schedulable on this vCPU, composition analysis choose to the regional composition analysis choose to increase the budget of the vCPU to reduce the starvation interval. This is how the abstraction overhead is introduced. So we revisit the composition analysis and notice that instead of inflating the budget, if we can make sure each vCPU can always serve its budget at specific time slot in each time unit. In this case, if this vCPU can always serve its results at the beginning of its period, then we can guarantee the starvation interval is no larger than 9, without increasing the vCPU's budget. So this will help us remove the abstraction overhead. We call this kind of vCPU as well-regulated vCPUs. In the dissertation, we prove that vCPUs are well-regulated vCPUs if they use periodic server mechanism to manage their budget, and if their periods are harmonic and release offsets are the same, and if they are scheduled under EDF scheduling and are schedulable, and the scheduler uses a deterministic priority type breaking policy. The first three conditions, we have shown that the first three conditions can be satisfied with the off-the-shelf Zen real-time scheduler. The last condition can be satisfied after we make a small modification to the real-time scheduler in Zen. Now, based on the well-regulated vCPUs, we prove that a harmonic task size is schedulable under EDF scheduling policy on that well-regulated vCPU if the vCPU's period is the minimum period of its tasks, and if the vCPU's utilization is the total utilization of its tasks. Now we have a new analysis to calculate a vCPU's parameters. So for the strawman solution, we can revise the step 3 which calculates vCPU's parameters. We can replace the original composition analysis with our new analysis to get the improved solution. Now, to understand how much performance improvement we can get, we evaluate the system with the same task set. So we use the new improved solution to allocate results for the same task site and get the green line here. As you can see here, we significantly improve the system utilization compared to the strawman solution. And we are also close to the flattened algorithm, which is an indication of the best performance we can get. The gap between the green line and the dark line is because of the VM boundary. So it seems that the improved analysis brings a lot of performance benefit to us. We want to know if the abstraction overhead-free analysis is enough to give us such good performance. So we consider another algorithm that uses the abstraction-free analysis but evenly partition results for cores. We get the yellow line here. As you can see here that without the heuristic resource allocation algorithm we proposed in our preliminary solution, the system's performance is not as good as the green line, the heuristic algorithm we proposed, the improved solution we proposed. So this gives us the this tells us that in order to get a significant performance improvement, we have to get to use not only the abstraction-free analysis, but also the heuristic resource allocation algorithm. Now we have demonstrated that our improved solution performs significantly better than Strawman solution and is close to the flattening algorithm. Is the performance benefit consistent? To answer this question, we repeat the experiment for different platforms and different task parameters and confirm that the performance benefit is consistent across different system parameters. We also measure the average execution time of different algorithms and found that our algorithm consumes a similar amount of time as the flattening algorithm does, and we can finish within 3 seconds. To recap, we provide the resource management mechanisms in real-time zone that can manage the CPU resource, share cache resource, and memory bandwidth resource. We propose a holistic resource allocation analysis technique to allocate the CPU, cache, and memory bandwidth resources for tasks. Evaluation demonstrates that we need both the abstraction overhead-free analysis and our proposed heuristic resource allocation algorithm to improve the system's performance significantly. To conclude, in this dissertation, we propose cache-aware real-time virtualization, which provides the timing guarantee for multi-core virtualization platform under the presence of cache interference. It has 4 building blocks: the private cache-aware composition analysis to analyze the private cache overhead impact, the dynamic cache management framework to mitigate the shared cache interference. To improve the system performance, we have the cache-aware scheduling analysis to co-schedule CPU and cache resource, and we have a holistic resource allocation analysis that allocates the CPU, cache, and memory bandwidth resource in a holistic manner. The first 3 building blocks has been published in conferences and journal. The last one we will submit to a conference and journal. So in my dissertation, I primarily focused on the real-time virtualization, which only covers the publications marked in green. During my PhD study, I also did other research. I also explored the research in other aspects of real-time virtualization and the cyber-physical system security. Thank you very much. I'd like to take any question.